Alright, Spinors and Twistors episode 2. Here we're going to compare different types of spinors to each other. Up until now, we have only been looking at Pauli Spinors. These are spinors that don't have any time component to them, and so therefore are not conducive to space-time. To address this, we will start studying a new type of spinor called a Weyl spinor. We're still in the phase of understanding spinors, but if you hang out with me until the end of this video, we're going to allude to twistors and conformal transformations also. But in this episode, we are going to cover the four main types of spinors, namely the Pauli Spinors that we've already been looking at so far, Weyl Spinors, Dirac Spinors, and the unusual case of the Majorana spinor. By the end of this video, we will get into a little bit of topology as well. I sort of heavy loaded the first episode so that we could get through Pauli Spinors relatively quickly. So let's review really quick. What we saw in the last video was when regular vectors were casted in the Pauli framework, rotations took the form of unitary matrices instead of orthogonal matrices. Unitary matrices have a whole host of unique properties and contain complex valued entries. We had to sandwich Pauli vectors in between two of the unitary matrices to get full rotations in this formalism. And this is what these rotations looked like. So the first thing to note here is that Pauli vectors are just the same thing as vectors, just casted in a different way. So what would it mean for such a Pauli vector to have a determinant of 0? Well, this doesn't mean that the Pauli vector doesn't exist because it still has x, y, and z components. It just means that if we were to look at this block sphere here, there would be no flag for any matrix to rotate around. And so we call this state a state of maximum entropy, or a completely mixed state. In other words, all of the states are completely mixed into one point that's centered in the block sphere. This is important because we're going to impose this determinant equaling 0 to help us understand and to help us get to Pauli Spinors. So let's go ahead and do that. So how do we do this? Well, we start off by noting that there will be no net spin state, as I mentioned before. In other words, the determinant of our Pauli vector is going to be 0. From this, we could see that we can get an expression for z. From matrix multiplication, we get 4 equations and 4 unknowns. We can then call a the square root of x minus yi, and c is the complex value of the square root of x plus iy. From this, we can calculate the rest of the variables and find that c equals negative b and that d equals a. So we have reduced the problem from 4 variables to 2, and we will rename the variables that we see in the literature to xi, and from this we can get x, y, and z in terms of spinor components, and vice versa. Okay, now we are ready to talk about Weyl Spinors, but before this I always like to go back to visuals and review along the way so that we don't get lost in the weeds. Just remember that this all came from experiments that were very physical and tangible in nature. We were able to see that birefringent crystals for photons and the Stern-Gerlach apparatus for electrons showed us how polarization and spin states can be rotated into what looked like very abstract spaces that were called the Poincare sphere and the block sphere. The Poincare sphere for photons and the block sphere for electrons. Antipodal points on each of these spheres referred to either different polarization states for photons in the case of the Poincare sphere, or different spin states for electrons in the case of the block sphere. From this, we were able to get the matrices that performed such rotations in these spaces, and we found that they were unitary matrices. Okay, now Weyl Spinors. The key thing for Weyl Spinors is that they are the relativistic version of Pauli Spinors because now we're adding an element of time. When we cast a relativistic 4-vector in the Pauli formalism, we use the identity matrix to get the following Weyl vector. Okay, so now we have the time incorporated into our vector. When we take the determinant of this Weyl vector, we get the magnitude again, but This time, setting the determinant equal to 0 will give us the condition that the time component of our vector is equal to the magnitude of the spatial component of the vector. And these vectors lie on the light cone, as we're familiar with from the special relativity. And this is called a null vector. Similarly, we can see that if the determinant is greater than 0, the time component of our vector is larger in magnitude than the spatial component, and such a vector lies inside the light cone, and this vector is said to be time-like. And last but not least, a space-like vector is one in which the determinant of our Weyl vector is less than 0. Okay, before we get into Weyl Spinors, we want to give some tribute to the man himself, as I'm a sucker for history and giving recognition to those who do the work in propelling science forward. Hermann Weyl was a brilliant mathematician. You might know him for his famous Weyl tensor in general relativity. This tensor was a means of attempting to understand how curved spaces could be described as being conformally flat. This was a magnificent feat in the world of general relativity, in my view, and deserves praise. The mathematics behind developing his famous Weyl tensor, which is the conformally flat version of the Riemann curvature tensor, was a brilliant achievement in the world of mathematics. There is a great website that you can visit called Weylman.com by William O. Straub, who focuses a lot on Weyl's work. There's a quote that I find particularly interesting from Weyl in his work titled Symmetry, and his quote goes something like this: "Symmetry, as wide or as narrow as you may define its meaning, is one idea by which man through the ages has tried to comprehend and create order, beauty, and perfection." We will go over the concept of the Weyl tensor in an animated series that I'm developing in general relativity, but let's get back to the topic at hand. We want to do the same thing that we did with the Pauli vector and decompose it into its corresponding Weyl Spinors. We will start off similarly with how we started in decomposing our Pauli vectors. We then get 4 equations and 4 unknowns, and note that A times C and B times D are completely real. That is, that there's no number I in their expression. So we could say that C and D are some scaled complex conjugate of A and B. We then use this fact, and the fact that B times C and A times D are complex conjugates of each other, to deduce the relationships between the 4 vector components and the Weyl spinor components. We can also calculate the phase factor by which the magnitude of the Weyl spinors oscillate. The exponential depends on time, but the difference only depends on the spatial components. From all of this, we could say that C and D are just complex conjugates of A and B, respectively. So we have reduced the problem again from 4 variables to now only 2. We rename the variables to match convention in the literature, so we have all these relationships. So I should be able to tell you the components of some 4 vector, and you should be able to tell me, or to be able to calculate, the components of its corresponding Weyl spinors, and the phase factor by which the magnitude of the spinor is oscillating. In the case of Pauli spinors, we can't calculate such a phase factor difference because the spinors need to oscillate in time, which these don't have. So if we were to put this all in the perspective of general relativity, say, we can imagine some vector space being concocted at any point in space and time. Such a vector is a 4 vector which can get placed in the Weyl formalism as a Weyl vector, which can then get decomposed into 2 Weyl spinors. And we will get back to this later, but the point that I want to emphasize here is that such mathematical objects can be regarded as fields, meaning that we can do this at any point in space and at any point in time. But now we run into kind of an interesting issue. If you've watched my series on general relativity, There are such things called covectors or dual vectors that act as maps for vectors to the space of real numbers. So is there such a thing for spinors? And the answer is going to be yes. Upper index vectors are normal vectors that we all know and love, while dual vectors are vectors that, without getting into the details of things, transform oppositely and have lower indices. Such details will be outlined in an animated tensor calculus playlist. The point, again, here is that we have vectors that have upper indices and dual vectors that have lower indices. Transforming between the two requires a metric. So what is the metric equivalent to for spinors? Well, we are just going to call this a spinor metric, and this is what it's going to look like. Because of the time component in the Weyl Spinors, again, their trace is not necessarily always going to be 0. Again, they can be time-like, space-like, or null. And because of this fact, we do not use unitary matrices to transform these vectors. We're going to propose that transformations of these matrices will preserve a spinor metric. To do this, we start off by proposing two Weyl spinors and transforming them together with our special linear matrices. We sandwich them between our spinor metric and demand that this metric does not change under such a transformation. And then we are on the races to find what all these variables are. Doing the matrix multiplication leads us to see that only two entries in the spinor metric that need to be non-zero are the off components, and that one is the opposite of the other. For simplicity, we just say that these two values are plus and minus 1. There's a lot of math going on here, but bear with me on this. So we have that because the trace of our Weyl vectors is not always 0, we have that dual vectors take the following form. We just apply the spinor metric. We transpose this because dual objects are typically regarded as row vectors. Contrasted with Pauli vectors, we can see that taking the Hermitian is all that is needed because this takes care of the transposing. We can see that dual Weyl spinors transform with the inverse of our special linear matrices, and Weyl spinors transform oppositely. So we have that Pauli spinors transform with unitary matrices and Weyl spinors transform with linear matrices, specifically special unitary matrices and special linear matrices. When we say special, we mean that their determinants are equal to 1. Such a difference is mathematically codified in the fact that there is a temporal component in the Weyl spinors, like we have noticed already. Furthermore, the unitary matrices that are used to transform Pauli spinors can be complex conjugated through these things that we're going to call C matrices. We can solve for the form of such matrices by doing matrix multiplication and then deducing that the off-diagonal components of these C matrices are all that matter. In the end, we can get the form of our C matrix. Such a transformation from U to U star is known as charge conjugation, and this matrix takes the form of our spinor metric. This suggests that such a metric not only plays a role in going between spinors and dual spinors, but also partakes in charge conjugating for Pauli spinors as well. We will revisit this concept later when we get to Majorana spinors, because this matrix plays a role in those types of spinors. In the case of Weyl spinors, this isn't the case. There's no such C matrix that conjugates our transformation matrices, and because of this fact, there turns out to be two copies of L matrices that we need to make this work out. And again, all of this fundamentally comes down to the fact that Weyl spinors are relativistic, meaning that there is a time component that renders them immune from always having a zero trace. The zero trace prevents these generators from being unitary, but we can make them unitary or have a proper set of charge conjugating matrices that work, and this is them. One side is the complex conjugate of the other side. Weyl spinors that the left matrices act on are left chiral Weyl spinors, and Weyl spinors that the right matrices act on are right chiral Weyl spinors. And so I took this table from Eigenkrist because I liked how he organized the differences between the left dual right and right dual Weyl Spinors, but I modified it a bit to be a little bit more complete. The T refers to taking the transpose, the star refers to the complex conjugate, and the dagger refers to taking the two combined, or the Hermitian conjugate. The key thing to realize here mathematically is that dualizing spinors means dropping their index, and the difference between right and left chiral spinors is a matter of putting a dot on the index. If there is a dot, then this is a right chiral spinor. Right chiral spinors are just complex conjugated left chiral spinors. Some sources will have different notation, but this is my favorite. Taking the transpose of spinors means turning them into a column if they start as rows and vice versa. Okay, now we've covered Pauli Spinors and Weyl Spinors. Now it's time for Dirac Spinors. But before I do this, I feel like I have to pay my obligation or pay my dues to Dirac himself. He was a brilliant mathematician. In my estimation, Dirac was most famous for his famous Dirac equation, and not the spinors themselves. This equation was discovered in 1928, and this equation contained his famous Dirac spinor in it. This is a series of coupled differential equations that formed part of the basis for quantum field theory, and we'll dive into quantum field theory in a little bit more detail on a separate playlist. But this equation predicted a new kind of particle, namely a particle with negative energy. To the physics world, this was a heretical idea, and to Ettore Majorana, who we'll talk about in a few minutes, this was actually wrong, which is very, very strange. But this equation was a feat of its own. We just want to get to the nature of the spinor itself that shows up in this equation and not derive the entire equation, because that's going to be a separate topic and that's going to be related more to quantum field theory. In this series, we just kind of want to look at the spinors and then go from there. And so the Dirac spinor is a combination or a coupling between a left chiral spinor and a right chiral spinor. And let's look at a little bit more details. What we want to note here is that when we combine a left chiral spinor with a right chiral spinor, we're combining a copy of the left and a copy of the right SL2C representations that we saw earlier. So in some sense, these objects cancel each other out, creating something that still has internal indices but is more complete, and we can think of these things as coupling and creating charge. It's for this reason that Dirac spinors describe electrons. It will be useful to show how the Dirac equation leads to the Pauli exclusion principle for electrons in general chemistry, but this is going to be a separate video. This is going to be a proof of their legitimacy and how they work, but not a topic of this video. We can do the same thing for dual spinors. And so we have two Dirac spinors. And I put just a reminder of what the left and right representations look like for these spinors, or for the transformations of these spinors. Because again, what we care about are the transformations of these things, not really the things themselves. In physics, what defines something as what it is how it transforms. And I really want to put emphasis on that. The Dirac equation is a bi-spinor field with two coupled spinors at every point in spacetime. And that will be the same case for Majorana spinors. So let's now talk a little bit about Majorana spinors. Majorana spinors have the unique property that they are their own antiparticles. The particles that these Majorana spinors describe have not been discovered in nature yet, but there's a lot of research and work going into attempting to try to find such spinors. So what is the idea behind them? Well, before we do this, again, I have an obligation to recognize the person behind such spinors. Ettore Majorana was something of a human prodigy and an enigma in and of himself. He was a mathematical genius, and by the age of 30, he had already made major contributions to the world of quantum mechanics, quantum field theory, etc. He is famous for rejecting Paul Dirac's notion of antiparticles. When Paul Dirac made his proposition that antiparticles existed in a sea of particles that we all can observe, Majorana said no, and he was famous for quoting in one of his works right after Paul Dirac made his proposition saying, "I reject the Dirac sea." Instead, Majorana proposed that particles with no charge were particles that were their own antiparticles. Unfortunately, he was reported to have gone missing in 1938, and no one knows what happened to him. Theories have been purported to claim that he fled to South America after or during or even before the war, because he went missing in 1938. Other theories have suggested that some fascist government, either Hitler's government or Mussolini's government, abducted him because he had some intel on atomic bombs being made. With that being said, he was as elusive as the particles he describes here. And let's go ahead and get started and take a look at Majorana spinors. We can recall from Weyl Spinors that we had constructed a spinor metric. Using this metric along with conjugating the components of the left chiral spinor changes our left chiral spinor into something that looks like a right chiral spinor but isn't quite there due to the negative sign. Because of this, we can write down another coupled spinor, but instead of having a left chiral spinor coupled to a right chiral spinor, we have two left chiral spinors coupled to each other, and this is what we call a Majorana spinor. Instead of a coupling between right and left, we have a coupling between left and left. And this is where the idea of particles being their own antiparticles came from. So Majorana's equation is very similar to that of Dirac's equation. The components of the spinor are just more constrained due to the claim that Majorana made, which was that if a particle has zero charge, then it was equal to its own antiparticle. Such a claim has yet to be disproven, but much effort has been placed into investigating Majorana's claim. Such a particle that has zero charge includes the famous neutrino. Current experiments are attempting to solve this age-old debate between Majorana and Dirac. Personally, and this is just my personal opinion, and this might sound heretical, but being someone who is half Italian and half Peruvian, I tend to err on the side of Majorana. My reasoning for this is not merely based on my national identity, but I think that we should tend towards logic that there should be fewer fundamental particles than more, and the idea of introducing antiparticles to me runs contrary to the idea of Occam's razor, but that again is just my opinion. So contrasted with Dirac spinors, which were rotating in this animation in opposite direction, Majorana spinors can be thought of as two coupled spinors rotating in the same direction. And so there we have it. Scalars, vectors, tensors, Pauli Spinors, Weyl Spinors, Dirac Spinors, Majorana Spinors, and all of their duals. Scalars can be thought of as a single component object, whereas vectors are multi-component objects. Vectors are added up in a unique way to construct tensors, or broken down to reveal spinors. Spinors come in roughly two different types: Pauli spinors, which are not relativistic, and Weyl spinors, which are. Due to the relativistic nature of the Weyl spinors, they come in two different types, which are right and left chiral. Combining two of each gives us Dirac spinors, where having two of the same will give us Majorana spinors. All of these spinors give a coherent and workable structure to quantum field theory. On the other end of this diagram, or on the right side of this diagram, is the arena of general relativity, where we deal with curvature tensors, torsion tensors, conformal tensors, lengthos tensors, and so much more, but this is going to be a topic for a playlist on advanced general relativity, which is in the works. The more you all support this channel, the more content like this will get produced. So with all of this being said, let's talk a little bit about topology, just to get our feet wet in this notion, because this is going to be important for twistors later. We can imagine bisecting a circle with a line. For every 1 point on the real projective line, which is what we're going to call this line, there are 2 points on the circle. And it is for this reason that we say that the circle is the double cover of the line. Instead of identifying a point on the line with points on the circle, we can just use the slope of the dotted line here. Steeper slopes correspond to points closer to the edge of the circle before the point gets teleported to the other side. The same thing can be done in 3D. A point on a plane in a 3D sphere can be specified with two slopes. This becomes harder to visualize in higher dimensions, but we can extrapolate this pattern out to accommodate for four-dimensional spacetime, where a point in spacetime is double covered by 2 points on a higher dimensional sphere. So why does all of this matter? This is a good place to start talking about twistors. We can see that the determinant of a special unitary matrix is the equation of a 4D circle with a radius of 1 if the alpha and beta encode coordinates in 4D spacetime. So it might be reasonable to think that insofar that these matrices represent a sphere, they double cover a point on a plane that bisects the sphere. And this plane is referred to as the real projective plane. Given that we see that SU2 matrices do indeed double cover a vector space, we can use this topology to model what is going on. And so the logic for twistors will be, for us, at the most simplest form, premise 1, Lorentz transformations are transformations in spacetime. Premise 2, spinor transformations double cover Lorentz transformations. In premise 3, Lorentz transformations are a special case of conformal transformations. In conclusion, there must be something that double covers conformal transformations then. Roughly speaking, the answer is going to be twistors. So this is going to require us to learn some stuff about conformal transformations. We're going to cover this in great detail because in the end we aim to understand not just spinors, but also twistors. In the videos to come, we are going to spend some time unpacking conformal transformations and consequently some conformal field theory as well. To do this, we will start with a very basic understanding of what a conformal transformation is. We are then going to go over its tensor formalism in the way that Hermann Weyl did back in the 1930s and 40s. We are then going to dive into the conformal algebra and its generators. Then we are going to get into the notion of split vectors, which will put us in the weird space of 6 dimensions, or in a weird 6-dimensional space, and then we will relate the two things to see how important conformal transformations are on the topic of twistors. This is a very difficult topic, but will be very rewarding in the end. We will have truly an in-depth understanding of the world as we go through these episodes. As we go through this series, I kind of want to think of twistors as Roger Spinors, if you will. All these spinor objects are named after some famous physicist, and given the fact that Roger Penrose came up with this theory, and he has been knighted, he's Sir Roger Penrose, I think that he should get more credit. The reason I want to call them spinors is because twistors will be able to be thought of as bispinors, just as Dirac Spinors and Majorana Spinors are. They are constructed by right and left chiral spinors, but they are related to each other through complexified Minkowski spacetime and through something called the incidence relation. And while the spinors that we have been talking about can be described by a Bloch sphere, we're going to need a Riemann sphere to make sense of twistors. And while the spinors that we have been talking about can be described by a Bloch sphere, we are going to need a Riemann sphere to make sense of twistors, or Roger Spinors as I would like to call them. Anyways, make sure to hit that like and subscribe button, and I will see you all in the next video.